this is heat. Fourth part, today we'll deal with calorie, specific heat, and also we'll discuss about the temperature and kinetic energy, and also we'll deal with the relation between the temperature and the kinetic energy also, right? So firstly we'll start with calorie, right? So if you look into the calorie, normally as you guys studied in the first part that heat has a CGS unit, right? CGS unit of heat is calorie, right? But coming to the calorie, calorie has a particular definition. Coming to the definition of calorie, it's very simple. The amount of heat energy, just listen carefully, the amount of heat energy, okay, the amount of heat energy that is required to raise the temperature of 1 gram of water by 1 degree centigrade. You need to remember this thing carefully, right? In this case, what happens is calorie is nothing but the amount of heat energy that is required to convert 1 gram of water to 1 degree centigrade, or else to raise the temperature, right? So just observe it carefully. For suppose I had taken a beaker here, right? So I put it over a stand. Now I put a Bunsen burner or a Bunsen burner. Now I lighted the burner. Inside I had taken just 1 gram of water, right? I had taken only 1 gram of water. Let's say 1 gram of water. It might be 5 or 6 drops maybe. And before I pouring the water, I just observed and calculate the temperature. It is at a normal temperature of 24 degrees centigrade maybe. Okay, let's consider 24 degrees centigrade. Now, if you observe the definition, it says the amount of heat energy that is required to raise the temperature of how much? 1 gram of water by 1 degree centigrade. Before it is 24 degrees centigrade, right? I just waited till it comes to 25 degrees centigrade, right? It comes to 24 to 25, which means water raises the temperature by 1 degree. Yes or no? It raises the temperature by 1 degree. To gain the temperature by 1 degree, it absorbs some heat energy, right? Yes or no? It absorbed some heat energy. That heat energy we'll call it as a calorie. What? The heat energy that is required to raise the temperature of 1 gram of water by 1 degree centigrade. Is it clear? Right? Just observe it carefully, Nana, right? Because you might get confused with the definition of a calorie along with the specific heat, because they both has a similar definition. Okay, but if you have in here, there may be little bit difference. Let me write the definition of specific heat first. If you look into this specific heat, right, the definition is also the same. It says the amount of heat energy required to raise the temperature of, right? If you look here, up to here there is no differences, right? Temperature of, here we have taken 1 gram of water, right? But here we will take unit mass of a substance. What? We'll take unit mass. Here in this case also unit means 1. Okay, same definition. But here there is a change in the specific heat, that is unit mass of a substance, but in calorie they had given us 1 gram of water, right? Unit mass of substance, none. You need to understand it carefully, because in calories we will deal with only water. Okay, and not only water, we will deal with different kinds of substances also, but here in the definition they had given us particularly the substance, that is 1 gram of water. But in this substance they hadn't given us the particular substance, right? We need to consider many kinds of substances here. Here the amount of heat energy required to raise the temperature of unit mass, right? You need to observe the difference, right? Unit mass of a substance by 1 degree centigrade. Okay, if you observe these two, same for here also. Here also we will take the beaker, we will put a stand, because without the stand the bowl might fall down, right? That is the reason. So if you put it like this, now I lighted the Bunsen burner again. Inside I had taken unit mass of a substance. In this case Not only water, we can take several kinds of substances as well, right? Like kerosene or petrol or diesel, anything you might take, right? So in this case I had taken some substance like petrol, right? We have taken a petrol here, there is O also, right? So here what happens is you need to observe it also carefully. 24 degrees centigrade to 25 degrees centigrade, okay. Here also 1 degree centigrade. Here also the same specific heat says the amount of heat energy required to raise the temperature of unit mass of a substance by 1 degree centigrade. But here 1 gram of water by 1 degree centigrade. Here the major difference here comes to the specific heat is we will measure the difference between two kinds of substances. Clear? For suppose if you consider here water in one hand and sea water on the other hand. If you consider these two, okay, they both have different kinds of substances, right? They both were not same. Water is drinking water we are dealing with. Sea water is nothing but the water that is present in sea. It is so salty, right? Right? So here in these two cases, they both have different values here, right? So let me tell you an example. Let's say if we consider specific heat, if the specific heat value of a substance is much lesser, okay, let's observe here. Let's say we have a lead and water, right? So the specific heat value of lead is much lesser compared to the water now, right? So the major difference comes here is if the specific heat value is lesser, it gains the heat energy much faster, right? If the specific heat value of water is much greater, right, that is the reason it gains heat energy much slower. Let's say here we will take two beakers here. In this case also we will do the same thing, right? Here also we will take a Bunsen furnace and we will fire it, okay. In the first beaker we have taken lead and in the second beaker we have taken water, right? So we will take some quantity, not only take 1 or 2 grams, we will take 10 ml or 20 ml, okay, let's say it's 20 ml, both were 20 ml now, right? Both the masses were same, right? And also we are giving the same heat energy. Now we need to look for the, just put a stopwatch here, right? Let's put thermometers inside, okay. Now initial temperature for both is 24 degrees centigrade and it is also 24 degrees centigrade, okay. After we need to wait for 5 minutes. How much time we need to wait? 5 minutes. After 5 minutes, just observe the readings in the thermometer. You will find something that is lead has a specific heat of lesser, okay. It has a less specific heat value than compared to the water, because water has a highest specific heat value, that is 1, but compared to the lead it is much lesser, right? So in this case what happens is if it has a less specific heat value, what happens is it gains heat energy much faster and also it loses heat energy much faster, right? In this case, now after we waited for 5 minutes, right, now this temperature might becomes up to 55 or something else, okay. But if you look into the water, it's still in 34 or something, because it has a higher specific heat value. Yes, if you observe the major difference here, lead gains the more heat energy. Yes, within 5 minutes, if you observe two substances, what happened here? One substance gains heat energy quickly than compared to the other one, right? So if you waited, let's say, let's put these two substances at same temperatures, right? Let's say first beaker contains lead, right? Again, we are not doing anything to it. Another beaker contains water. First beaker contains 50 degrees centigrade, second beaker also contains water, it is also at a temperature of 50 degrees centigrade, right? Now if you consider these two, they both were at the same temperature, what? 50 degrees centigrade, right? We don't do anything, just keep it like this and observe, okay. We need to wait for, again, how much time? 5 minutes. And after 5 minutes if you observe, what happens? What might gonna happen here? As you guys know, if the value of specific heat is lesser, it loses heat energy quickly. If the value of specific heat is higher, it loses heat energy slowly, okay, not that quick. Here in this, what happens is, in this, within 5 minutes it comes to 25 or something, but after 5 minutes also it is still at 45 or 44. Yes or no? You could easily observe, because let's take a general example of water, right? For suppose if you are inside the kitchen, right, you're just boiling the water because you just wanted to take a bath, right? Now we will put here something, okay, we have taken some water here, right? Now I started heating it, right, and after thorough heating it up, it becomes 100 degrees centigrade. Okay, let's imagine water has a low specific value. Which value? Low specific heat value than compared to the other substances. Let's imagine like this, right? It's not true, but just imagine. Now what happens is, within fraction of seconds it comes to 100, okay. After it gets 100, you want to fill this water into your bucket, right? Okay. While you are filling it into your bucket, it gets cooled to 0. Okay. Then you need to take a bath in the kitchen as well. Okay. That's because if it has a low specific heat, none. But if it doesn't have, that is the reason it takes much time to cool it. Yes or no? Yes, I think you got a clear idea about the specific heat also, right? So normally, I think you guys know about the heat. Heat has a formula. Heat is equals to ms delta T, right? Here m represents mass, S represents specific heat, and delta T represents change in temperature. What? Change in temperature. Okay. So in this case, now heat, okay, we'll put H here, right? H. So instead, in some books H is also written. In our textbook it is represented with the letter Q, right? Now in short form we'll write it as, okay, wait a second. In this case, we'll write as Q is equals to ms delta T, right? Now I think you know the terms here, right? So here in this case, we'll derive the formula for specific heat, right? So simply m is multiplying S and delta T also multiplying S, right? We'll send these two to the other side. When it is multiplying, it goes to the other side. What happens? It is going to divide, right? So simply m is going to divide and delta T is also going to divide. So finally we got a formula, that is S is equal to Q by m delta T, right? If you look at the units carefully, coming to the SI unit, as you guys know, SI unit of heat is joule, as we discussed. Mass as SI unit of kg, and temperature difference is measured in Kelvin, right? Joule per kg Kelvin, right? So this is the SI unit for specific heat, that is joule per kg Kelvin. On the other hand, we have a CGS unit also. CGS unit, heat has a CGS unit of calorie per mass as CGS unit grams, and delta T, as I said before, in some books it is written, they will take degree centigrade also, right? So now CGS unit is calorie per gram, degrees centigrade is the CGS unit for specific heat, right? So coming to the applications of the specific heat, so let me tell you some applications here, right? So I think you guys know about samosa, right? Samosa, right? So if you consider the samosa, right, it is stuffed inside with some curry, I hope so, right? Inside it is filled with the curry, right? So if you observe this carefully, what happens is, when the samosa, it is still in oil, okay, when it gets boiled, and then I think the cook might remove it from the bowl and put it inside your plate. Now when you touch the outside layer of the samosa, you tend to feel it is cool, right? So you feel it is cooler, so you just take a bite. Now what happens? You tend to feel outside layer is cooler, but inside it is still hot, and your tongue gonna say it, right? You might feel, oh my god, right? It's so hot, right? So that is going to happen because if you consider the outside layer is made up of a substance. It is a substance, right? That substance has a specific heat value. it is lesser compared to the specific heat of value of a substance that is inside the curry. The curry has a specific heat value of higher compared to the specific heat value of the outer layer, right. In these two cases, what happens here is outside layer specific heat value is lesser, so it gets cooled quickly, right, but inside layer it is not so cool, so it is still hotter. I think it's very clear, I hope so, right. So this is one of the example for specific heat. So if you consider one more example, let's say let's consider summer season. Let's consider this is the summer season, right. So if you went to a beach, I think you know about a beach, right. In the beach you tend to see these are the rivers, let's say, and we tend to find some of the sand, that is nothing but river bed we'll call, right. In the river bed you are standing, let's say you are standing on the river bed and this is the river here. Now what happens is, from the morning to the evening time, what happens is this whole both, if you consider these both, right, they both absorb heat energy from the sun, yes or no, because it is the summer time. What happens is the temperature might be in a peaks, yes. So what happens, the temperature might get absorbed by these two, that is nothing but river bed. On the other hand, simply we'll say it is sand, we'll take a sand here, right. This is river, simply we'll take the substance that is water, right. Now exactly in the evening session at 7 o'clock, right, you went at 12 o'clock, and you observed something, that is it is hotter and the water is also hotter, right. And then you went to 7 o'clock, and if you consider the river bed, right, you are putting a steps here without any shoes or something, which means you guys were walking with a barefoot, right, your voice barefoot, which means you tend to feel a little bit cooler here, okay. That's because it comes to its normal position. But if you went to the water, what happens is it is still hotter. Why there is a difference between these two? Why is it happen here? It happened because sand has a less specific heat value. As you guys know, water still has a high specific heat value. In this case, the heat energy absorbed by the land loses quickly, but the heat energy absorbed by the water doesn't lose, right. That is the reason it gets cooled quickly, it doesn't, okay. I think you got the difference between these two, right. So these are some of the applications that are related to specific heat. We have different kinds of applications here, right. In day to day life, we will deal with several kinds of applications that are related to the specific heat, okay. So we will deal with the final thing, that is the difference, major difference between the kinetic energy and the temperature, right. So let's observe here. Let me tell you. Firstly, we will take temperature, right. I think we discussed about the temperature in the part 2. So temperature is nothing but the degree of hotness or coldness of a body is called temperature, okay. Here temperature means the degree of hotness or coldness of a body is called temperature. I think we discussed about it, right. But coming here, there is a relation between the kinetic energy and the temperature. So you need to know more about the kinetic energy now, right. In the 9th standard, you guys have studied, not only 9th standard, you guys have studied in your 7th and 6th standards also, but you haven't known it is a kinetic energy, right. But let me tell you it clearly, that kinetic energy, okay, right. So suppose if you consider any body that is in motion, right, okay, if you consider any object, let's say we'll consider a car here, a wonderful car we have drawn, right. Let's say the car is moving towards this side, right. So now if the object is in motion, let's say the car is an object, right, we'll consider this car as the object. If the object is in motion, we'll consider, if an object is in motion, it possesses an energy, that energy we'll call it as a kinetic energy, right. every moving object nana, it contains an energy. That energy we'll call it as kinetic energy. On the other hand, you might get doubt, that is, I think I haven't heard about the potential energy also, sir, right? So coming to the kinetic energy, if an object is in motion, it contains an energy. That energy we'll call it as a kinetic energy. Let's consider a fan. If the fan is rotating, which means the fan possesses an energy. Which energy it is? Kinetic energy, right? For suppose if you consider a person, he is walking. Walking means there is a movement in the object, right? Which means he possesses an energy. Which energy? Kinetic energy. Let's say if you consider one more person, let's say he is cycling. Now tell me which energy he possesses? Kinetic energy, right? Now coming to the potential energy here, let me tell you, potential energy is nothing but, here kinetic energy means if an object is in motion, it possesses an energy, right? So here potential energy depends on position. What? Position. It depends on the position. For suppose, let me tell you something. For suppose you are on a tree. Wow, wonderful tree here we have run, right? It is a tree of a, it looks like something. Okay, let's say it is an apple, right? So there is a small branch. Now you just wanted to cut this apple and eat it. So you just walk upside and sit on that branch. Now you just wanted to, you are trying to do something. What? You are trying to cut the apple, right? At that time what happens is the branch broken down. Now what happens? You tend to fall down, right? You fell because you are at a particular position. Yes or no? You are at this position, which means you are possessing some energy. Okay, you are not moving anywhere, but you are at that position, which means you are having energy. That energy we'll call it as a potential energy, right? Let me tell you clearly, when he is at the top, he possesses an energy, potential energy. Okay, when the branch cuts it, he started moving, right? That potential energy converted into kinetic energy. He is in a position, right? But when the branch cuts, what happens? He started falling down, right? Which means he possesses an energy. That energy is nothing but kinetic energy. In the beginning he has potential, and the end it gains, let's say it is 10. Okay, here normally potential energy has a formula. Potential energy is equal to mgh, and kinetic energy also has a formula, half mv square. Okay, we'll deal with those things later. Okay, it's not these formulas were not that much important here. But coming to the temperature and kinetic energy, okay, right? Let me tell you a little bit interesting thing here. Okay, let's say we'll take two beakers. We are dealing with heat energy, right? We are not dealing with the physics overall problems part. We are dealing with heat energy. Let's observe it in the form of a heat energy. Let's say we have taken how many beakers? Two beakers, right? In the first case and in the second case. In the first case, we have taken water that to 200 ml, and in the second case also we have taken water 200 ml, right? When you switch it on, what happens is, in the first case the gas is completed, which means the stove just puts off, right? But in the second case it is still glowing, which means it is going to do what? The heat energy we have giving is going to absorbed by the particles inside the water, and there might be rise in temperature, right? It is in the beginning 24, and after some time it going to become 35. So we still waited it to become 70 degrees centigrade, right? But it's still at 24. Why is the difference happened here? Because in this beaker we are giving heat energy, but in this beaker do we give heat energy? No, right? It is still at 24 because we just put off the stuff. Okay, so now we did a little bit interesting thing, that is we will take food colors. You know what food color, right? Right? Any color you want. Okay, it doesn't depend. We will pour 2 drops in each beakers. Okay, just pour 2 drops of food colors inside these 2 beakers, and you need to wait and observe something little bit interesting happen. Okay, you haven't put anything inside, right? But you just waited for that food color to spread all over the beaker. Clear? Now what happens is, in this beaker the color, food color spread fastly as compared to the second beaker. Why is it happen? In the second case, temperature is 70, but in the first case, temperature is 24. In the second case, 24, right? The particles will move. Okay. Suppose this is one particle and this is one particle. At 24 degrees centigrade, they are moving. Okay. They are moving much slower. But in the second case, the temperature is 70 and the kinetic energy might be greater compared to the first case, right? So they might go much faster. Sir, in the first case, the particles move slowly. If the particles are moving, then it possesses which energy? If there is a movement, it possesses kinetic energy. Clear? In this case also what happens is, if we raise the temperature, the moment of the particles also raised. Yes? Yes? By this, we simply say temperature and kinetic energy were directly proportional. Which proportional? Directly proportional. Which means, if temperature increased, kinetic energy of the particles also increased. Clear? So, from this, we should easily conclude that temperature and kinetic energy both were directly proportional. Is it clear? So, with this, I think we have completed our topics. Okay, major topics we have completed, and then we have a little bit problem session, that is principle of method of mixtures is one, and then we will deal with specific heat of a solid, right, and then we have the activities, right. Okay, we will complete overall activities in one video. Clear? So, that is it. Thank you.